Okay, so I'm going to start out with particle kinematics. Number 15. And this one, there's a Ferris wheel. We're using a coordinate system like this. The radius is 5 meters. There's a clockwise angular velocity of 1.5 radians per second. And also a clockwise angular acceleration of 2.5 radians per second squared. And the passenger is at this location. And we want to calculate the velocity. So if I call this point P, what's the velocity of P? What's the acceleration of P? And then so now imagine that this Ferris wheel is on a truck or something, on a vehicle that's moving. Well, I guess it could be a truck if it's on a hill or whatever. So what's the acceleration of P if the acceleration of the center is 5 - 3 meters per second squared? So this is the point C. All right, well, let's figure out first the angular velocity and angular acceleration of the body, and then let's figure out the r vector for that point P. We're going to need that for all of these. So the angular velocity vector, the angular velocity is this way, and so your thumb is into the board. X cross Y has to be positive Z. So if your thumb is into the board, into the page, that's the negative Z axis. So this omega vector is 0, 0, negative 1.5.
This may sound like a stupid question. What is angular velocity as opposed to velocity in the z direction?
Angular velocity is, it's telling you how quickly the orientation is changing. So angular velocity is like if anybody, me, if in 2 seconds I go through this many radians, whatever, 26 degrees or something, okay, then the amount of angle that I go through divided by the elapsed time is the angular velocity. That's just the way it's defined. So the right-hand rule is always the use of the right-hand rule is always a relationship between some kind of rotation and a vector, okay, and a perpendicular vector. That's what the right-hand rule is for. And there's just a lot of places where it's useful to do that. And so in this case, the rotation is what we see, and the vector is, well, this way, and the vector is into the page.
There's not actually any velocity in the z direction.
No, that's right. That's right. So any plane motion, any motion that's happening in the XY plane only, all of the rotational quantities are in the z, are parallel to the z axis. Okay. It's how fast the orientation is changing. So it's an angle divided by a time. If you go through, you know, pi over 2 radians in 1 second, then pi over 2 over 1 radians per second is the angular velocity. Well, it's, you know, and it's a limit, so it can change. What I did was sort of like an average angular velocity, but that's the idea. Sure. Okay, and then the angular acceleration, which is just how quickly the angular velocity is changing. Use the right-hand rule again. It's in the negative z direction, so alpha is 0, 0, negative 2.5. And then the r vector, yeah, thanks. And then the r vector is the vector that goes from the center of the circular path to the point of interest. So if this thing has a radius of 5, that's negative 5, 0, 0.
Because of where?
Right. So now the velocity of that point P, we can just use the equation for velocity that says velocity is omega cross r. And so that's 0, 0, negative 1.5 crossed with negative 5, 0, 0. And that is 0, 7.5 positive 0. This is meters per second. And now does it make sense that the direction of that velocity vector is in the positive y direction? Yeah, if this thing's rotating this way, then that point is moving up. And now for B, we have to use the watermelon equation. The acceleration of P is equal to alpha cross r plus omega cross quantity omega cross r. So that's 0, 0, negative 2.5 crossed with negative 5, 0, 0 plus 0, 0, negative 1.5 crossed with the quantity omega cross r, which is what we just calculated here for velocity. So I'm going to write this as 0, 7.5, 0, but remember that this just comes from the watermelon equation. That's because this is omega cross r. And you get that the acceleration of P is 0, 12.50 plus 1.5 times 7.5, 11.25 positive in the x direction. And so the answer is 11.25, 12.50 meters per second squared. Yes. Okay, well, we can talk about that after, but really, I mean, you might as well just be doing this with your calculators, and then you never have to think about it. And then part C, now we're assuming that the center is accelerating, okay? So the way we're going to do part C is the acceleration of P relative to the ground is equal to the acceleration of P relative to the center plus the acceleration of the center relative to the ground. This is what we just calculated in part B. What would be the acceleration of that point P if the center was fixed? Yes?
What does that mean, the center of the carousel? Does that mean the whole carousel?
Yeah. Right, it's on a vehicle or something. And the center relative to the ground we're given now is 5, -3, 0. And so this is 11.25, 12.50, plus 5, -3, 0. And that's 16.25, 9.50. Any questions about that? Well, it's both in part B, because in part B we're assuming that the center of the carousel isn't accelerating. So the acceleration of the center of the carousel is the acceleration of the ground. Okay, like you could fix a camera to the center of the carousel, or you could fix it to the ground. They would measure the same acceleration. Okay. Any other questions? All right. Well, let me go on to the next thing that is sort of related to this. So that's rolling without slipping. And we're going to talk about this rolling along a flat surface. It doesn't have to be horizontal, but it has to be flat. And if you choose a coordinate system with the positive y-axis straight out of the surface, so we're talking about like an incline, there's the center. The coordinate system has the y-axis pointing from inside the surface to outside the surface, and that means x is that way. Then the velocity of the center is negative omega r 0, 0. And the acceleration of the center is negative alpha r 0, 0. And so what we're talking about here is we're assuming that the angular, like a positive value of the angular velocity and the angular acceleration are counterclockwise. You can think of those also as so omega and alpha are the z components of the angular velocity and angular acceleration vectors. And r is the radius of the wheel, ball, etc. Nope. So if so the way it works is if they are positive and it's rolling this way, then you can see that the velocity and acceleration would be up the ramp in the negative x direction. If those are negative and it's rolling this way, then these will come out. Then omega and alpha are negative, and these come out positive, and that means it's rolling that way. So it's pretty intuitive. Okay. Okay, so let's say that we have this thing rolling horizontally. And let's say that we have an angular velocity of 3 radians per second. And let's say that it's slowing down. So if it's slowing down, the angular acceleration is the other way. So let's say this is 10 radians per second squared. Let's say the radius of this disk is 0.5 meters. And we want to calculate the velocity and acceleration of this point P.
Is angular velocity always slowing down? I mean, always negative when it's slowing down, no matter where?
It's not always negative. They always are the opposite direction if it's slowing down. That's right. What are the angular? No, not angular. What are the velocity vector and acceleration vector of that point P? Okay, well, first let's calculate the angular velocity and no, there's no reason. Is there a reason to do that? Well, first, this is the center, okay? So for rolling without slipping, maybe the first step would be let's calculate the velocity and acceleration of the center. Why do we need to do that? Okay, we're trying to calculate the velocity and acceleration of that point P, right? And the velocity of that point P relative to the ground is the velocity of P relative to the center plus the velocity of the center relative to the ground. Okay. Yeah, right. So if this was just like the Ferris wheel and it wasn't touching the ground, and this was at rest, the center was at rest, then it would just be a circular motion problem to calculate the velocity and acceleration of that point. But as this thing's rotating, the center has a velocity and acceleration that we can get from the from the rolling without slipping equations. And so we're going to set it up this way, where this is circular motion of P around C, and this is rolling without slipping. And we're going to do the same thing with the acceleration. So the acceleration of P relative to the ground is equal to the acceleration of P relative to the center plus the acceleration of the center relative to the ground. Okay, so the velocity of the center relative to the ground is equal to negative omega times r, 0, 0. What's that omega value? What? Oh, so you have to be careful with the sign. Think of the right-hand rule. Negative. So we have negative 3, negative, this negative, of negative 3 times 0.5. Okay. 0, 0. And so that's positive 1.5, 0, 0. So that's the velocity of the center observed by the ground. Well, one negative is because that's the formula. Okay, and then the second one is the component. And then let's do the acceleration of the center relative to the ground too. So that formula is negative alpha r, 0, 0. What's alpha? Positive 10, yep. So this is negative of positive 10 times 0.5, 0, 0. And so that's negative 50, 0, negative 5, 0, 0. And this is meters per second squared. Now we're going to calculate the velocity and acceleration of the point P relative to the center. So that's like assuming that for a second we're going to treat it like the center is fixed and just do that circular motion calculation. So the velocity of P relative to the center, what equation are we going to use for that? For acceleration, it will be the watermelon. For velocity, it's just omega cross r. Yep. So what's the omega vector? Zero, zero, negative 3. Yep. Okay. Again, I mean, we sort of already figured it out. We just used it in a different form. Right-hand rule says that at the end of the page, our coordinate system for these kind of problems is always y-axis out of the surface, x-axis parallel. So z-axis is coming straight out towards us. So this is 0, 0, negative 3. crossed with the r vector. What's the r vector for that point P? That's the vector from the center of the circular motion to the point we care about. 0.5. Yep, exactly. No, that's it's the x component. You're doing it right with your hand, but not y. Yeah. So negative 0.500. Take the cross product, and you get 0, 1.50. And now for the acceleration, we'll use the watermelon equation. So the acceleration of P relative to C is equal to all ripe watermelons will rot. So we have the omega and the r, we just need the alpha. What's alpha as a vector? 0, 0, 10 in the positive z direction. By the way, this thing where rotational quantities are vectors perpendicular to the rotational motion, I mean, I understand why that seems weird, but that's going to come up over and over again. That's the way moments are calculated, angular velocities and accelerations, lots of ways of measuring rotational, orientations are done that way. So don't shoot the messenger, but you're going to have to get used to it. Because like with a rotational quantity like this, I mean, think of a better way to define, like, how do you define how it's rolling within a vector? This is a good way, but that's not a vector. How would you represent the components of this rotating thing? Well, as you know from those of you who've taken Calc 3, one of the easiest ways to represent a plane is to represent it with the normal vector. And that's basically what we're doing here. We're representing the plane that this is rotating in using a normal vector. And then the magnitude of that normal vector is the magnitude of the angular quantity. So yeah, if you just think about a plane, like what's the most concise way you can represent the orientation of this plane? Well, it turns out that the way to do it is come up with a vector that's perpendicular to it. And then with just 3 components, that tells you everything you need to know about the orientation of this plane. And it works the same since rotations are instantaneously planar motions. These perpendicular angular quantities are basically just telling you the orientations of these planes by giving you the normal vector. Okay, so alpha is 0, 0, positive 10. The r vector is negative 0.5, 0, 0. And then we're adding that to 0, 0, negative 3, crossed with omega cross r, which we just calculated is 0, 1.50. So for that first term, we get 0, negative 5, 0. For that second term, we get 4.5, 0, 0. And so the acceleration vector is 4.5, meters per second squared. And now we can finally use that relative motion equation. So the velocity of P relative to the ground is the velocity of P relative to the center plus the velocity of the center relative to the ground. The velocity of P relative to the center is 0, 1.50. The velocity of the center relative to the ground is 1.500. And so the velocity of that point P is 1.50 meters per second. And so if there was like a light on that point of the wheel as it went around, and you're just tracking the motion of that light, at the instant that the wheel is at that far edge, at that far side, the instant that point is at the far end edge of that wheel, it's moving at this angle at 45 degrees. Okay. Tangent to the path at that instant would be at 45 degrees. And then the acceleration of P relative to the ground.
Wait, are you saying that that's at the instant in the right on the diagram?
Mm-hmm.
Not moving up and down.
That's right. So because of the relative motion, if it was just in circular motion around a fixed point here, it would be going up. But the center is moving that way, and so it's actually moving at 45 degrees at that instant. If you track this motion, it looks like, track the motion of a point, it looks like McDonald's forever. So acceleration of P relative to the ground is acceleration of P relative to the center plus acceleration of the center relative to the ground. Acceleration of P relative to the center is 4.5, negative 5, 0. Acceleration of the center relative to the ground is negative 500. And so add these two up, you get negative 0.5, negative 5, 0. Well, any questions about the math? On these rolling problems, anytime it asks you for velocity or acceleration of some point on the wheel or the ball or whatever it is, you're going to have to use relative motion. And anytime it says rolling without slipping, any of that, you know you're going to use those two equations for what the center is doing. Okay, that just has to be the case. The easiest rolling without slipping problem you could have would just ask you about the velocity or acceleration of the center. But most of the time it's going to ask you for velocity or acceleration of some other point, and you'll have to get it for the center and then use relative motion to find what's happening for that other point. Why would you care about this? Well, if you were starting a bicycle fender business and you were trying to figure out how you could use the least material and make the lightest possible thing that would block the most dirt coming off of your wheel, then you'd want to know what the acceleration was of all the different points on the wheel, so you'd know where where the mud was most likely to be shaken loose, and with looking at it like this, you could compare those different values at the different points and say like, okay, there's a lot of acceleration happening here. That would send mud into an area between here and here. There's not much happening here. And, so what if you aren't starting a bike fender business, or you're planning to, but not this year? Then is this useful? Well, the general answer is it's useful anytime you're trying to use Newton's laws, because this is all kinematics, but the connection between kinematics and kinetics is acceleration from Newton's second law. Okay, so like, no matter what else you know about the kinematics, I always think of acceleration as like the skyway, like you're trying to get to the 6th floor on the IDS, and I don't know if there's a skyway to the IDS, but and you're on the 4th floor of the eating at Crave or whatever downtown, Well, it would make more sense if you could just go straight from the 4th floor to the 4th floor of the IDS and then go up to, but you can't do that. There's only one skyway, So wherever you are, you have to go down to the 2nd floor, take the skyway, and then go up. And that's acceleration in trying to get from kinetics to kinematics and vice versa. You got to always go through acceleration. And so that's why often that's what you're going to be asked for. Any questions about skyways? Okay, well, if you have more questions about skyways, the answers can be found at your local library. All right, well, let's stop there. So we'll do second quiz on Friday.